So let's talk about continuity on a closed interval. This is kind of sometimes weirds people out. And to be honest, it freaks me out half the time too. One thing we say about continuity, remember, the value must exist. We must have a value. We must have a limit. And they must be equal to each other. So let's look at the graph here below. We want to know, is this function considered continuous at x equals a and x equals b? Now, if you notice, at those values, the limit cannot exist. So we would think this would make this like really kind of simple, that it cannot be continuous at a and b. But there's a rule, a special rule, only for closed intervals. If we have a function on what we call a closed interval, a and b, hard brackets, not soft brackets. Remember closed intervals? Those are your hard brackets. So a function is continuous on a closed interval if the function is continuous on the open interval. So what this says, that if the function is continuous all throughout, in between, if the function is continuous from a to b all throughout, then we're going to say it can be considered continuous on the closed interval. In other words, if the single-sided limit, if I'm approaching from the right or from the left, if the single-sided limit exists at the endpoint and the function is continuous throughout, then we consider the function continuous on the whole graph. So it's kind of like a rule that says, listen, we have to deal with endpoints anyways, so we're just going to say we're always continuous at an endpoint. That's what that says. We are always continuous at an endpoint. So let's look down here. We want to determine the continuity of this graph. In other words, we want to find out for what values would this be continuous. Now, for those of you in the know, that's a circle right there. It's really a semicircle. So here's the graph right down here. We can see this. We want to determine the continuity between -1 and 0. So we just want to find out if it's continuous there. And so we can check this. Ready? If I say, so I'm checking the single-sided limit. I'm going to approach -1. Now, if I want to find the limit as we approach -1, notice there's nothing on the on the left side here. I can only approach it from the right. And from here, we are approaching 0. And then I can do the same thing from 0. There we go. The limit as x approaches 0. Now again, at 0, there's nothing to the right of 0 on our graph. So I can only approach this from the single side. And that's what this says. We're taking a single-sided limit. And if we limit there as we approach from the left, we're approaching 1. That's going to equal 1. Now we're not talking, now notice these are different values, so it's not like does the limit exist, the left equal the right, because we're approaching two different x values, so that we shouldn't expect them to have to become the same. But what this does tell us is, because this is a closed interval and the limit exists on the one-sided limits, then this function will be continuous on the domain from -1 to 0. So we can say, therefore, f of x is continuous on that interval. On the domain -1 to 0. We're not going to use soft brackets. It's just like a very special case for us. And there's our answer right there. Now, a way we can tell if it's continuous also on the inside, because remember, it does say as long as it's continuous throughout, no holes, no gaps, no jumps. That's what really continuity means. No holes, no gaps, no jumps. Okay? So let's take a look here at an AP question. Consider the function. This function right here. Now, I'm going to have to work mine on a separate sheet of paper here, but you can work on your own. For f of x to be continuous, it asks us to find the value of k. Now, this came on the AP test. And they gave us the choices. 0, 1, 2, D and E, or Mr. Warnell's awesome. That actually was a choice on the AP exam. So we want to find out, what does k have to be to make this continuous? So, well, really kind of simple to do. We're going to talk a lot more about these type of examples tomorrow. If I want to find k to be continuous, well, what are we saying? That these have to be equal to each other. So in other words, that the limit as I approach, remember we talked about this from the other day, that's actually a limit value, that this has to approach the value k. If I want them to be equal, they have to be equal to each other. In pre-cal, you would have done something like this. Sine x over x equals k. And you would solve for k at x equals 0. Now, here's the problem. Oh no, I can't plug in. And the reason for that is because, well, sine of 0 over 0, that's a major issue for us. That's our indeterminate. So the only way we can actually solve this one is using limits. So this is actually an example of why we need limits. I want to find out what does k have to be to make this true at x equals 0. So I have to use a limit. So I'm going to use my limits instead. The limit as x approaches 0 of sine of x over x equal to k. And that's easy. That's just a rule. This is 1 equals k. So the answer is going to be B. I hope you guys enjoyed the video. Please smash that like button. I'll see you guys tomorrow. Bye.